Welcome to the course Compiler Design. In this lecture, now we'll discuss the last concept of syntax directed translation, that is implementing L-attributed syntax directed definitions. So in this first, we will discuss translation during recursive-descent parser, so which is top-down parser, then on-the-fly code generation, then again L-attributed SDDs and LL parsing, that is for top-down parsing. Then bottom-up parsing using L-attributed SDDs. Okay, now implementing L-attributed SDDs, the following methods do translation by traversing a parse tree. The first one is by building the parse tree and annotated parse tree. This method works for any non-circular SDD whatsoever. Non-circular means so there is no graphs in dependency, there is no cycle in any dependency graph. Then second one, build the parse tree and add actions, semantic actions in the productions. So in our previous topic, we demonstrated one example for the given expression prefix notation. So using semantic actions in the parse tree. So using the same, build the parse tree, add actions, and execute the actions in pre-order. This approach works for any L-attributed definition. So we discussed how to turn L-attributed SDDs into an SDD in our earlier topics. Now, in particular, we discussed how to embed actions into productions based on the semantic rules of such an SDD. This also we discussed in our previous concepts. Okay, now the third one, by using recursive-descent parser, which is top-down parser, one of the method of top-down parser. That means in the given grammar, for every variable in the left-hand side of the production, we can define recursive procedures. So using the same. So using recursive-descent parser with one function for each non-terminal, the function for non-terminal, let us say capital A, receives the inherited attributes of capital A as arguments and returns the synthesized attributes of the non-terminal A. Then the fourth one, generate code on the fly. That means using recursive-descent parser in between whenever code is required. So you can use instantly. Then fifth one, implement an SDT in conjunction with an LL parser. So syntax directed translation with combination of the predictive parser, that is LL1 parser. So the attributes are kept on the parsing stack and the rules fetch the needed attributes from known locations on the stack. So then the sixth one, implement an SDT in connection with LR parser. So that is bottom-up parser. This method may be surprising since the SDD for an L-attributed SDD typically has actions in the middle of productions, and we cannot be sure during an LR parser that we are even in that production until its entire body has been constructed. We shall see, however, that if the underlying grammar is LL, we can always handle both the parsing and translation bottom up. Okay, now let us see in detail. First one, translation during recursive-descent parsing, that is top-down parser. A recursive-descent parser has a function for non-terminal capital A for each non-terminal, as discussed in top-down parser that we know. So we can extend the parser into a translator now as follows. First, the arguments of the function capital A are inherited attributes of the non-terminal A. Then the return value of the function A is the collection of synthesized attributes of non-terminal A. So in the first point, what we mentioned, same. Okay, now in the body of function A, we need to both parse and handle attributes. So the first step is decide upon the production used to expand the function A. Then check that each terminal appears on the input when it is required. We shall assume that no backtracking is needed. So in top-down parser, without backtracking, that is one of the difficulty. So you can overcome that backtracking. So, but the extension to recursive descent parsing with backtracking can be done by restoring the input portion upon failure, whenever failure occurred. Then the next point, preserve in local variables the values of all attributes needed to compute inherited attributes for non-terminals in the body, or synthesized attributes for the head of the non-terminal. Synthesized attribute always used for the head left-hand side variable, whereas inherited attribute in the right-hand side grammar symbols. That we know the difference between inherited and synthesized attribute. Then fourth point, by call functions corresponding to non-terminals where we define in the body of the selected production, providing them with the proper argument, since the underlying SDD is LAttributed, so which is suitable for top-down parser. We have already computed these attributes and stored them in local variables. Okay, now let us see with one example. Now consider the SDD and SDT for while statement in our programming languages. S derives while condition, then statement, where S is the non-terminal that generates all kinds of statements, including if statement, assignment statement, and others. In this example, C stands for conditional expression, a Boolean expression that evaluates either true or false. This is a normal programming language while statement production. Now, by taking SDD and SDT, so with recursive descent parser, how this can be implemented. Now, let us see first the syntax directed definition for while statement. S derives while condition, then statement. First, we are taking the semantic rules. Let us say L1 equal to new, then L2 equal to new, then S1 dot next. Here, this one right hand side. This is the inherited attribute. S1 dot next equal to L1. We are storing in this new function. Then C dot false condition. First, if it is false, it calls S dot next. If condition is true, it calls L2, the new method. Then S dot code equal to the left hand side head of the production. S dot code equal to, by labeling first L1, label L1, then by calling C dot code, then label L2, the synthesizer attribute S1 dot code. So here, except the new method and false and true conditions, so remaining this S dot code equal to, this is same as our inherited attribute semantic rule in SDD. But because here recursive descent parser means by defining methods, then same SDD by enclosing within curly braces. Now those are all becomes semantic. Now this will become semantic actions. Why? Because this is SDT for the same while statement. Now here you can see L1 equal to new, L2 equal to new, C dot false equal to S dot next, C dot true equal to L2. Now all these actions are embedded within curly braces. Next group is S1 dot next equal to L1. Next group is S dot code equal to this entire one. So the third semantic rule is included in one. Now finally, so this is group 1, then this is group 2, then this is group 3. Finally, 3 semantic actions corresponding to semantic rules. This is SDT for while statement. Okay, now let us see the implementation with pseudocode. A pseudocode of the relevant parts of the function S shown below. So implementing while statements with a recursive descent parser. So string the function S with arguments label next. Then we are defining S code and C codes as strings, local variables holding code fragments. Then we are defining labels L1, L2, the local labels. Then the condition, if current input equal to, the condition is if current input equal to token, while advance the input to the next symbol, then check the left parenthesis is the next on the input and advance. So this is the pseudocode. Now next step is you have to call the new labels L1 equal to new, L2 equal to new. Then define C code. So for a variable C code equal to C of next comma L2. Then check right parenthesis is the next on the input, then advanced. Then call S code equal to S of L1. Then return the code with labels. Label L1 C code and label L2 S code. In the above, whatever the SDDs we used. Else, it calls other type of statements. This is the pseudocode for implementing while statement with a recursive descent parser. Then the second method is on-the-fly code generation. So the construction of long strings of code that are attribute values is undesirable for several reasons, including the time it could take to copy or move long strings. In common cases, such as our running code generation example, we can instead incrementally generate pieces of the code into an array or output file by executing actions in SDT. So on-the-fly code generation means by splitting into pieces of the code into an array or output file. Then whenever required, by executing the semantic actions in syntax-directed translation, those can be incorporated. That is the on-the-fly code generation. Now let us see the example. Syntax-directed definition for on-the-fly recursive descent code generation for while statement. So recursive descent parser in the above we already mentioned. Same by using on-the-fly. We can modify the function of while statement to emit elements of the main translation s.code instead of saving them for concatenation into a written value of s.code. Then the revised s function is shown below, the above pseudocode algorithm. So void s label, there are labels L1, L2. Now if current input equal to token, advanced input, check the left parenthesis is the next input symbol advanced. Up to this same, L1 equal to new, L2 equal to new, up to this same. So then here you can see. Now we are printing label L1, then we are calling C of next comma L2. Now we are splitting the pieces. Then check right parenthesis is the next on the input and advanced. Then print label L2. Here, this is the new print statement. For this is the print for L1, this is the print for L2. Then calling C of next comma L2, then S of L1. So here, pieces of codes. Else, other statements are. That is the only difference. Okay, now similarly, SDT. The above syntax directed definitions are enclosed within curly braces. Now that is becomes SDT. Now the semantic rule becomes semantic actions. Now the C SDDs while first open braces L1 equal to new, L2 equal to new, then C dot false equal to S dot next, then C dot true equal to L2 print label. This is one semantic action. Then second part S dot next equal to L1, then print label L2. For S1, no semantic actions. Then coming to LAttributed SDDs and LL parsing. Suppose that an LAttributed SDD is based on LL grammar, that is predictive parser, and that we have converted it into an SDD with actions embedded in productions. We can then perform the translation during LL parsing by extending the parser stack to hold actions and certain data items needed for attribute evaluation. Typically, these data items are copies of the attributes. In addition to records representing terminals and non-terminals, the parser stack will hold action records. Now we will use the concept of parser stack where we discussed earlier, which represents actions to be executed, and the synthesized records which holds synthesized attributes for non-terminals. Okay, now we use the following two principles to manage attributes on the stack. First one is the inherited attributes for non-terminal A, which can be placed in the stack record that represents that non-terminal. The code to evaluate these attributes will usually be represented by an action record immediately above the stack record for the non-terminal A. In fact, the conversion of LAttributed SDDs to SDT, which ensures that the action record will be immediately above the non-terminal A. Then second case, we will use synthesized attribute. Synthesized attributes for non-terminal A are placed in separate synthesized record that is immediately below the record for the non-terminal A on the stack. Now this strategy, whatever the strategy we mentioned here, places records of several types on the parsing stack, trusting that these variant record types can be managed properly as subclasses of stack record class. So in practice, we might combine several records into one, but the idea is perhaps best explained by separating data used for different purposes into different records, like pieces of code. Then by using action records, what action record contain? Pointers to code to be executed. Actions may also appear in synthesized records. These actions typically place copies of synthesized attributes in other records further down the stack, where the value of the attribute will be needed after synthesized record and attributes appear or popped off the stack. You have to pop from the stack. Okay, now let us see the same while condition, expansion of S according to the while statement production. S there is while C S1. So now in the stack representation, first S, the left hand side header will be on the top of the stack. Then next below of this one, next equal to X, calling this one. So now this figure shows the situation as we are about to use while production to expand S, because look ahead symbol on the input is while. The record at the top of the stack is S, and it contains only inherited attribute, that is S dot next, which we suppose has the value X. Since we are now parsing top down, we show the stack top at the left according to our usual convention. Okay, now let us see expansion of S according to the while statement production with all actions. First while, this one while is on the top, then left parenthesis, that will be the next time that will be on the stack. Next action we are defining S next equal to X, then L1 label 1, then label 2 initially empty, then condition C false value true value, then closed parenthesis, that is on the next, then action calling for AL1, then AL2 labels, then at last S1 actions next. So now here we are defining what is L1 L2 using the parser stack. L1 equal to new, L2 equal to new, stack of top minus 1 dot false equal to S dot next, or stack of top minus 1 dot true equal to L2, stack of top minus 3 dot all equal to L1 AL1, then stack of top minus 3 dot AL2 equal to L2, then print label L1. So this is connected to this action, that is L1 L2. Then for this AL1 AL2, stack of top minus L dot next equal to AL1, then print label AL2. So now this is the complete diagram which shows the expansion of S according to while statement with parser stack actions. Now the explanation is shown here, whatever we mentioned. Okay, now this is another one, expansion of S with synthesized attribute constructed on the stack. So now here S next equal to X, these are all on the top. Now synthesize S dot code, code equal to data equal to. So here only synthesized attributes are used, the remaining all are same. Now similarly, the complete specification with the synthesized attribute, while left parenthesis action, then condition, then synthesize C dot code, this is the new, then right parenthesis, then S1 value. So here everything is synthesized. Now we are defining after this, next one is this one, synthesize S1 dot code, next synthesize S dot code. So remaining all are same as in previous one. Okay, now similarly, bottom up parsing of LAttributed SDDs. Now previous one is top down parsing, that is LL. So here we can do bottom up, every translation we can do top down. More precisely, given LAttributed SDD on an LL grammar, we can adapt the grammar to compute the same SDD on the new grammar during LR parser. The trick here we will use, the trick is the one of the method with the 3 parts. First, start with the SDT constructed earlier, then which places embedded actions before each non-terminal to compute its inherited attributes. Then action at the end of the production to compute synthesized attribute. Second one, introduce into the grammar with marker non-terminal in place of each embedded action. Each such place gets a distinct marker, and there is one production of any marker with M derives null. Then next one, we have to modify the action A if marker non-terminal M replaces it in some production. Now, like A derives alpha, A, this is the action we mentioned earlier, beta, and associated with M derives null. And action A dash that copies as inherited attributes of M and then attributes of variable A or symbols of that action terminal A needs. Then compute attributes in the same way as terminal A, but makes those attributes synthesize the attribute of M. So this point we already discussed above. Now let us see one example. Here A derives BC in an LL grammar. The inherited attribute B dot I is computed from inherited attribute A dot I by some formula B dot I equal to F of A dot I. That is, the fragment of an SDT we care about is A derives B dot I equal to F of A dot I. Now this is the action included in the production. Now BC remaining same, right side. Now we introduce marker M with inherited attribute M dot I and synthesizer attribute M dot S. The former will be a copy of A dot I and latter will be B dot I. The SDT now will be written as, now let us see. So A derives M BC, here M is the marker. Then M dot I equal to A dot I, then M dot S equal to F of M dot I. Now this is SDT action is embedded here. Now let us see the SDT for while statement, what we discussed as previously, same is shown here. Now for this, by using this grammar with semantic action, S derives while MC, N S1, where M derives one marker null, then N is the another marker null. Both derives null productions. Okay, now for this, see the stack implementation with parser stack. So LR parsing stack after reduction of null to marker. Now first question mark, nothing is there. Then S dot next, then while, then open braces, then M marker will be placed, then true, false conditional value, then labels. Code executed during reduction of epsilon to M. So first L1 equal to new, L2 equal to new, C dot true equal to L2, C dot false equal to stack of top minus 3 dot next. Now let us see stack just before reduction of the while production body to S. So here also see everything same. Now here N S1 dot next, then S1 dot code. Now this will become the top before S. Okay, now let us come to the summary of this lecture, what we discussed till now. Implementing LAttributed SDDs. First, translation during recursive descent parsing, then on-the-fly code generation, then LAttributed SDDs and LL parsing, then bottom-up parsing of LAttributed SDDs. For this, the reference is how to section 5.5.1 to 5.5.4. So till now, the first part of third unit, that is semantic analysis, is completed. So next class, we will start the next phase of compiler, that is the fourth phase of compiler, intermediate code generation. Now I stop here.